Hi, in this video I will talk about the stellar evolution of large, medium, and small stars. All stars form in a cloud of gas and dust called a nebula. After the collapse of the nebula, a protostar is formed. The protostar continues to move faster and increase its temperature as it condenses. When the core is at a temperature where nuclear reactions can occur, it starts to convert hydrogen to helium. A star will stay this way for 90% of their lifetime. This is called the main sequence phase. A star can stay in the main sequence for 20 million to 80 billion years. A medium-sized star like the Sun will stay for about 10 billion years. After a star has burned up all of its hydrogen to helium, the temperature in the star increases so that it can burn helium to carbon. The energy generation rate in the shell increases, which causes the star to swell up into a red giant. In a small star, the core will ignite in a helium core flash. A bigger star's process will be less extreme. Burning helium to carbon is much quicker than burning hydrogen to helium. After this process, the next thing depends on the size of the star. A small star is less than 8 solar masses. The next step in the stellar evolution of a small star is the core of the star will contract, but will never reach temperatures hot enough to burn carbon. Once the star reaches electron degeneracy pressure, it stops expanding. Electron degeneracy pressure occurs when the lowest level is filled. Other electrons move into higher energy states, which increases the temperature and increases pressure. After this, a white dwarf is formed. During this time, the thermal pulse expands the outer layers of stars until they are ejected completely and become a planetary nebula. A larger star's process will be much different. Just like a small star, a large star will start contracting. It will reach a temperature that will burn neon. Eventually, elements like iron will form in the core. After this, the only thing left for the star to do is collapse. In a star with a core mass less than 3 times our Sun, the result of the collapse will be a neutron star. The stopping contraction when the star becomes a neutron star causes a supernova. With a huge star with a mass greater than 3 solar masses, the collapse will become a black hole. In this diagram, we can see what I just talked about. On the top, with the low and medium mass stars, it starts with a nebula, then the main sequence phase, then red giant, next a planetary nebula, and lastly a white dwarf. On the bottom, where it is labeled high mass stars, it starts with a nebula, then main sequence, then red supergiant, next a supernova, and then finally, for a high mass star, it becomes a neutron star, and for a very high mass star, it becomes a black hole. 90% of all stars are in their main sequence phase. All stars in the main sequence phase are burning hydrogen to helium. The rate at which a star burns up all their hydrogen depends on the size of the star. The larger the star, the less time it spends in the main sequence, and the smaller the star, the longer it spends in the main sequence. Main sequence stars are in a state of hydrostatic equilibrium. Hydrostatic equilibrium in a star occurs when the star's core creates pressure which counteracts with the force of gravity. When you compress a gas, it exerts a gas pressure back and resists compression. This process itself does not keep a star from collapsing, but with the combination of this and the energy created by the fusion of hydrogen keeps the star from collapsing in on itself. A red giant star is a star that is dying. About 1/10 of stars are red giants. When a star becomes a red giant, it has used up all of its hydrogen in its core, so it starts burning helium to carbon. Most of the bright stars we know about are red giants because of their luminosity. Red giant stars live on average 0.1 to 2 billion years. Medium-sized stars will become a red giant near the end of their life, while large stars will become red supergiants. The biggest red giant ever discovered was VY Canis Majoris. Some examples of main sequence stars are the Sun, Sirius A, Achernar, Alpha Centauri, and Altair. Some examples of red giant stars are Aldebaran and Mira. An example of a red supergiant is Betelgeuse. Example of a white dwarf star is Sirius B. The size of a red giant varies from 100 to 1,000 times the size of our Sun. A white dwarf star is a core remnant of a star. Even though a white dwarf is relatively small, it has a mass similar to the Sun. About 0.4% of all stars are white dwarfs. Some characteristics that make up white dwarf stars are they have a temperature of about 8,000 to 40,000 Kelvin and a luminosity of about 0.1 to 1.4 times the luminosity of the Sun. White dwarf stars are the final stage in stars with a mass that is too small to become a neutron star. After the Sun becomes a red giant, it will become a white dwarf. White dwarfs have used up all their fuel because white dwarfs are so small, they're very hard to detect. White dwarfs are usually a part of a binary system. When the Sun becomes near the end of its life, it will start to swell up into a red giant during this process. The temperature on Earth will increase until the Sun completely engulfs the Earth.